A wonderful good morning, ladies and gentlemen. I welcome you here at the technical forum at the group exhibit Hydrogen, Fuel Cells and Batteries here at the Hanover Fairground in the year of 2015. Every 50 minutes, I'll present to you interesting presentations regarding the hydrogen and fuel cell industry. And for that, you can also come and relax and have a coffee or drinks. They're all on the house. There's a lovely lady walking around and serving you these drinks. For now, I'd like to present to you the next topic, which is the influence of ceramic powder quality on processing and SOFC performance. And for that, please welcome with me on stage the product manager of CerPoTech, Mr. Guttorm Syvertsen-Wiig. Big hands, please.
Thank you very much. I'm here to talk about powders and the importance of starting with high quality starting materials when you want good performance, and how flexible powder manufacturers can be, and actually how much you can influence yourself how you get powders from us. So just a short presentation of our company. We're called Ceramic Powder Technology, or CerPoTech for short. So we produce high quality complex oxide powders of many different materials, as we'll come back to. Why we started was that we're a spin-off company from the university in Trondheim. And the research group there saw that it was difficult to obtain commercial powders of the quality they wanted and the specific compositions. So they decided to purchase a spray pyrolysis unit and build up their own small-scale powder production facility. And then you have much better quality than they found, and also they can tailor-made their own materials. And then the word spread, and their partners and friends wanted this powder as well, so they decided to start up a company. So we're located in the middle of Norway, in Trondheim, and the technology is based on spray pyrolysis of aqueous solutions. So in the brief history, it's in 2003. The first unit was installed at the university. In 2007, the company was founded, and in 2013, 2 years ago, we were able to move out from the university and build up our own pilot production facility outside the university campus. So what can our powders be used for? As long as you are in need of a complex oxide with some functional properties, we are basically interested in that. We are originating from a group working on fuel cells and membranes and that kind of materials, typically perovskites. So they're typically where we have our main customers and partners, but also other energy technologies such as batteries, supercapacitors, superconductors, and so on. Other types of applications includes gas separation membranes, both for hydrogen and oxygen separation, syngas production. We're also made some catalytic materials, photocatalytic materials based on titanium oxide. And also on electronics, lead-free piezo ceramics is quite a hot topic at the moment, since lead has been banned. However, it's still a lack of good substitution or materials to substitute the lead-based materials today. But we are involved in several research projects and have partners that are working closely on this. And also we make custom-made materials for any application, so we don't judge you for what you're actually going to use the powders for. And we also have some production of targets for PLD or sputtering sport. We're also heavily involved in R&D activities, especially on international level and the European Union. So we are right now part in 5 projects. The METPROCELL project is about making proton-conducting fuel cells with metallic support. We have a DEMCOMER project, which is anything to do with gas production, syngas and catalytic reactors. EVOLVE. It's also a fuel cell materials project, working to optimize the anode, making it more robust. And we have the MS Copper, where we develop photocatalytic coatings to be antimicrobial, for instance, for doorknobs in hospitals and so on, to prevent disease spread. And Coatley project, where we're developing composite coatings for the bipolar plates in PM electrolyzers. And we have a new project starting now in a couple of months on zinc air batteries. So our production facility is located in Trondheim, where we do the whole process from raw materials, dissolving salt and so on, spraying, and then post-processing of the powders. Today we have a capacity of around 4 or 5 tons, depending on which material we're producing. We're still limited by nature, and that meaning solubility of the elements in water. And for a typically medium batch-sized batch of 10 kilos or 20 kilos, we have a lead time of 4 to 6 weeks. Can be shorter. And it's a wide range of compositions, which I'll come back to. And we also have still a strong collaboration with the university. So we have access to quite a large number of different analysis equipment and techniques. So the core of our business is the spray pyrolysis unit, our working horse. So it starts out where we are dissolving different elements in water, stabilize this, and often adding some secret ingredients to make sure you have a stable solution. Because if you have some precipitation, you don't end up with a phase pure powder in the end, and you have no control. Then this solution is sprayed through the chamber and collected and dried, and the powder is collected at the end. And here you have a large number of parameters you can vary to tune particle size, surface area, and so on. So this is kind of a menu, a list of what we can work with. So all the green elements here we have experience with, and can combine these into different materials. We also have some other materials we can work on, such as silicon and phosphor and bismuth, but for several reasons we have chosen not to do this, mainly because they tend to form glassy phases at high temperatures, where that might ruin our equipment. And also, for instance, silicon is not wanted in other materials such as ionic conductors. So how does our powder look like? On the top here you can see what is actually happening inside the pyrolysis unit. You start up with small droplets, some tens of micrometer in diameter. The water is evaporating, forming a shell of metal salts. that partly decomposes into oxides through the furnace. For many of the materials, the time of flight inside the furnace at high temperature is not enough. So then we have a second step to remove organic residues and to form a single-phase material. And due to the evaporation of the water, you naturally have these hollow spheres that need to be ground down. So on the bottom left, you can see how an example of how these spheres looks like, because this is also something we can tune, the size of these and the thickness of the shell and so on. And then we mill it down, and on the middle down here you can see typically particle size of these powders. And the crystallite size can vary from 10 to several hundreds of nanometers, and the particle size is typically sub-micron, a few hundred micrometers. This also is depending very much on which material we're talking about, because thermodynamics is playing a minor role here. And also we can modify the temperature and time we're using to optimize the properties. So the materials have very high phase purity because we have very exact and good control of what we're actually putting into the furnace, and then we're getting all out. The powders are very homogeneous because of the small particle size and the small reaction distances, making complete reactions quite easy. And the stoichiometry is very, very exact, and we don't really have any source of contaminations except for our raw materials. That's also kind of driving the price. You can get as pure raw materials as you want if you're willing to pay for it. There's an example of the particle size distribution on the right, which is narrow and sub-micron, which also give rise to very good sintering properties of the powders, meaning that you can reduce your sintering temperature, and for an industrial process you'll save a lot of time and money doing that. So an example for an oxygen separation membrane, a benchmark test done by SINTEF, Technology Institute in Norway, where CerPoTech powder is the red powder, and you have some co-precipitated powders from another powder supplier in blue. So first, the phase purity is higher for the spray pyrolyzed powders compared to the other one. This might or this has effect on both properties and sintering behavior and so on. So as you can see here, you can actually reduce the sintering temperature by up to 200 degrees for the spray pyrolyzed powders compared to the co-precipitated powders. And all this again gives quite large effect on the actual oxygen ion transport through the membrane. That also can be caused by density gradients or maybe inhomogeneous powders, and of course the secondary phases that ruins your ionic conductivity. Another example on the cathodic example, this is from one of the projects we're part of, the VOLD project. This is LSCF powders, lanthanum, strontium, cobalt, ferrite, showing that different synthesis routes gives different results, and also these results are probably different if you try the same powder another time due to the processing conditions. So the phase purity, grain size, conductivity, and the size of the particles, because you need a lot of active triple phase boundaries, all affect these results. So it's important to actually know which powder you have, and that even if you have the same particle size distribution and surface area, you don't necessarily get the same results. Another example for strontium titanate doped with lanthanum, where you have a huge effect on the conductivity. For the spare products, powder has about 1 order of magnitude higher conductivity than similar or the same material made by solid state synthesis. Here also the picture is maybe not saying all the truth, because these materials, the thermal history is very important, because the defect chemistry depends on whether you have had exposed the material for reducing atmosphere or oxidizing atmosphere. One example on how the evolution of the phase purity or actually the crystallite size and phases on temperature. So down in the bottom here is an X-ray diffractogram showing the peaks of a quite well-known spinel material, magnesium aluminate, showing that you almost have amorphous powders when it's coming out from the furnace. And going up in temperature, you start to grow the crystallites, achieving higher or larger particles. And this is something we can tune, and when we are working with partners or customers and they desire a specific surface area or a particle size, we use these kind of experiments to do this. So basically different materials has different properties due to thermodynamics and kinetics, because you have cation diffusion and the melting temperature, and these physical properties play a role. So down on the left here is just a comparison of different materials calcined at approximately the same temperatures, but you'll get all the way from a specific surface area of from 1 or 2 square meters per gram and up to 30, 40 square meters per gram, just by changing the composition. Also here on the right, you can see the effect of calcination temperature on the specific surface area of a couple of materials. So you can, if you want a surface area of say 10, then we need to go to 950 degrees or something for the strontium titanate to achieve this. Also we can use milling of these hollow spheres to tune both surface area and particle size. So this is a case study on lanthanum chromite doped with strontium, where we had some target specifications of D50, the average particle size, between 1 to 2 micrometers, and the specific surface area measured by BET was supposed to be 2 to 3 square meters per gram. And then we both used different calcination temperatures and different milling times, showing that we actually achieved these numbers quite good. So that's all I had to say today. Feel free to drop by the Norwegian booth just over here. There are also some other companies related to hydrogen production and storage and other things. Thank you.
Thank you very much also from my side for taking us on a journey into the work of CerPoTech. It was an honor for us to watch here. Are there any questions from the audience at this time? Okay, everyone still needs to wake up. Okay. Once you're ready and you finish your coffee, you can visit CerPoTech at their booth number B60 at the Norwegian booth. Thank you very much.
Thank you.
Our next topic will be the use of waste hydrogen. And we'll talk about the Power Up project, and for that we'll hear the representative of the European Hydrogen Association. We'll hear Ms. Marieke Rijald, and that will be in 20 minutes time at 11:40.